So our last lesson in Unit 5 is over 3-8, and the topic is linear approximation. So if you printed out the notes, you're going to need to put this pre-example, if you will, somewhere. So I want to give you a little bit of background before I go over the information in your notes and the examples in your notes. So linear approximation is used to approximate values without using your calculator. So we can get pretty darn close to values without the use of our calculator by use of derivatives. And the general formula for linear approximation would be L of x, so your linear approximation in terms of x, so it's a function in terms of x, is equal to f of a, I'll talk about what these values are in a minute, plus f prime of a, here's our derivative, times x minus a. Now there are some people that will let this value right here be f prime of a times the change in x. So this right here is your change in x. This is, x is the value that we're trying to approximate, and a is the value that's really close to this value that we're trying to approximate. So x minus a is that change in value from what we're trying to approximate to what we're using to approximate it. But generally I like this form better, so I'm going to erase this and go from there. Okay, so for instance, what if I wanted to approximate the square root of 80? 80 is not a perfect square, all right? So I'm going to say that we're going to approximate the square root of 80. Now without a calculator, that's a little bit difficult. In Algebra 1, you might have been taught to find a value, a perfect square that's less than 80 and a perfect square that's greater than 80, and then decide, kind of guess and check, and it was a bit of a shot in the dark, and you could get somewhat close to it within a tenth or two, but we can actually get even closer using this formula here involving derivatives. So A is going to be our point that is close to 80 that's easy to work with. In other words, I want to find the closest perfect square to 80. So I'm going to let the closest perfect square to 80 would be, what, 81. And then we're going to let x equal 80. So our x is 80. And our easy number to approximate is 81. All right, so then we need to find our overall parent function. So the parent function that we are working with is going to be, take the 80 out, and we would have f of x, let's say, is equal to the square root of x, right? And then we have a derivative here. We would want to find the derivative of this. So f prime of x is going to equal something that you might, since we work with square root of x a lot and we take the derivative of the square root of x a lot, you might just want to remember that the derivative of the square root of x is 1 over 2 times the square root of x. How did I get that? Well, remember that x can be written as, or the square root of x can be written as x to the 1/2. So to find the derivative, you're going to take 1/2 in front of x, subtract 1 from the exponent, so you get negative 1/2. And so here's your 1/2 here and 1/2 here. To make this exponent positive, you're going to put it in the denominator with 2. So here it is in the denominator with 2, and it becomes x to the positive 1/2 when you put it down here, which is the square root of x. So I choose to use 1 over 2 square root of x. So then let's go ahead and write out this, giving all the values here that we have. So our linear approximation is equal to f of a, well, our function is the square root. Our a is 81 plus our derivative is 1 over 2, and it's the derivative with respect to a. So our a is 81, so square root of 81. And then times our x is 80 minus our a is 81. So we get equals, square root of 81 is 9 plus 1 over 2 times square root of 81 is 9 times 80 minus 81 is negative 1, which equals 9. And then this negative 1 times the 1, I'm going to make this minus right here. So I get minus 1 over 18. So it becomes 8 and 17/18. So that is the actual exact approximation. That is the exact value of the square root of 80. Well, I take that back. That's our approximation. This right here is our approximation of the square root of 80. So I'm going to go ahead and put into my calculator the square root of 80, which is approximately equal to, I'm going to put that in our calculator, 8.944278, and it keeps going, but I just wanted to put it out that far to you. This, if you put this into your calculator, 8 plus 17/18, you get approximately 8.94 repeating. So you can see that we have gotten out to 944, and then the rest of it's not the same. So we've gotten this approximation out to the 1,000th place. That's pretty good. So that's pretty much what we're going to do today. We're going to use this function, and we're going to approximate a bunch of things. Now, one thing that I'm not going to concentrate on is percent of error and over and under estimation, just because I don't want to take the time to do it. But for instance, here, our value that we're trying to find was 80, and we chose 81 to approximate it. That means we went over 80 to 81. So this is an over approximation. Okay, so we are going to change our topic to be 3-8. All right. And then we're going to want to highlight a couple things here. So we've looked previously at the first derivative is the same thing as the slope of the tangent line. So that's something that I want you to highlight here. So the straight line that appears at a given point has a slope equal to the derivative of a, and that's that slope of the tangent line. And again, you can see here's that linear approximation function, f of a plus f prime of a times x minus a. And you can see here that they're using f of x. Oftentimes we use L of x. It really doesn't matter. So don't focus on those types of things. Okay. Then I'm going to glance over a couple things here. Suppose f is a differentiable function at a point x equals a. So we're going to use that a value, if you recall, to approximate x's value. And so we want to find the difference between x and a right here for our approximation. So again, you see us using this function as a way to approximate the closest value to our x. And I don't want to talk about the error. Let's look at our visual right here. Let's look at the visual of how they came about with this equation. And I don't expect you to memorize this or anything, but I just want you to see visually what's happening. So right here, this is our tangent line right here. So let's label that as tangent line. So there's our tangent line. And then let's say that this right here is our exact value that we're trying to find. So this right here is our exact value. So that's our x, or our f of x. Okay. Then we are going to use the value of a which would be, so here's your A, that's our approximate value, and here's your X. That's why this is our exact value. X would be on this function here. A is also on our function, but it's also on our tangent line here. So this tangent line, this point right here on this tangent line, this point right here is our linear approximation value. So you might want to write that in there. So this point right here is our linear I'm going to abbreviate that, approximation value. Value. I can get the L in there. And so you've got this distance from here to here, and this distance from here to here. So remember, this is your change in y, and this is your change in x, and it creates the value for the slope of the tangent line. So if you were to set this up, you would end up getting the slope of the tangent line being f prime of a. So for instance, I'm going to do this down below. F prime of a, which is the slope of your tangent line, would be equal to your change in y over your change in x. And our change in x in this case is x minus a. So here's your change in y, here's your change in x. And if you were to solve this by cross multiplying, so I'm going to put this over 1, and if I cross multiply, I get change in y is equal to f prime of a times x minus a. So this value right here, this value right here is this value right here. So that is how we came up with that value, in case you're wondering. All right, what else do I need to show you on here? I think that's really about it. But visually, that's what we're trying to do. We're trying to minimize the difference between these two values here, and using that as our approximation. So here we go. So here you can see that this is the procedure that we're going to use to find a linear approximation. So I'm going to use the procedure that I just did in finding the approximation of the square root of 80. So when we found the square root of 80, there are some things that we didn't do. We didn't write it in point slope equation form, but there are a lot of these that you do need to do that. So we're going to have to write in point slope form. So instead of C, I prefer A, so it should be A f of A. Remember, f of A is your y value. And then you're going to isolate your y and rename the equation as L of x. So we have to actually find our L of x equation and then substitute your values into that equation. And then we are not going to do the overestimate or underestimate, and we're not going to find the error, and we're not going to do 6. So for our purposes here, we're going to stop at 1 through 3. For right now, we're stopping at 1 through 3. Okay, so then let's move this up and look at example 2. So let's go ahead and go through these steps for 2. Now let's look at what they gave us. So you've got to read through your function, you got to read through your equation or your problem that they gave you. So the function f is twice differentiable. So that means you can do the second derivative, where f of 3 is equal to -2. So they have essentially given you a point, right? So that f of 3 equals -2 is a point. So remember, if we're going to write the equation of a line, we need a point and a slope. So our point here is our x value is 3, because that's what we're inputting, and we got a y value, our output, of -2. So let's continue. Then f prime of 3 is equal to 5. Remember, the first derivative is slope. So f prime of 3 is your slope. So f prime of 3 is equal to slope, which is equal to 5. So those are all givens. And then the second derivative of 3 is equal to 1. So the second derivative is extra. So we don't need that at all for our purposes. It's just extra information that's not necessary. Write the equation of the tangent line. So we've got the slope of the tangent line is 5 and we have the point. So we can go ahead and find that equation, and instead of just finding the equation and replacing it and rewriting it as L of x, I like, well, maybe I'll go ahead and do that anyway. So I'm going to write, I'm only going to write the point slope form once, and then from then on, you're going to have to remember that I'm using y minus y sub 1 equals m times x minus x sub 1. That's point slope form of a line. And so we're going to substitute into here our values. So I know that my y value is -2, and my x value is 3, and my slope is 5. And so I'm going to take care of any double negatives, so this double negative becomes one big plus. And then I'm going to distribute the 5. So I got y plus 2 is equal to 5x minus 15, and then subtract 2 from both sides. I get y equals 5x minus 17. And then L of x, so that means that L of x is equal to 5x minus 17. So that is the equation of our tangent line. And they're going to use that equation to find the value of 3.1. Okay, so we're going to find L of 3.1, supposed to be parentheses, equals 5 times 3.1 minus 17, which is equal to -1.5. So that one's a pretty simple one. So linear approximation will do a great job of estimating values for a function, provided that you stay within that neighborhood that's close to the number that you're approximating. So when we were trying to approximate the square root of 80, we stayed really close to 80 by choosing 81. But if I had strayed far away from 80 and chose a different value, now our chance of error becomes greater. And the question is, well, the issue is the further away that we move from the number that we're trying to approximate, the worse that approximation becomes. And that's reasonable, that makes sense. While there's no easy method to determine how near or far away we can move from our point of tangency, we can predict the amount of error to give us an idea of how good the approximation models the actual value. That's the part in our notes today that we're not going to focus on and we're not going to really look at. But we are going to look at a famous linear approximation that's used to describe vibrations, pendulum motion, and is also used as a method to simplify formulas in optics. Okay, so let's look at y equals the sine of x at x is equal to pi over 3. So here's some of your issues that some of you are going to have is you don't remember your pre-calculus and your unit circle. So you're supposed to know what the value is of the sine of pi over 3, because if x is pi over 3, we're finding the sine at pi over 3. So you're supposed to know that the ordered pair corresponding to this angle is 1/2 square root of 3 over 2. So if you remember your unit circle, and I'm not actually drawing the circle, but I'm going to draw the quadrants. So pi over 3 is in the first quadrant, and I'm going to make a triangle out of that. And here is your angle measure right here. That's supposed to be an arc. Oh, goodness. That was terrible. Sometimes my stuff does not cooperate. Okay, so anyway, my angle measure here is, if I can write tiny, pi over 3. I still don't like that. All right, so that's my angle measure, pi over 3. So what degree is pi over 3? 60 degrees. So if you recall that your side lengths across from the 60-degree angle should be radical 3 here, 1 over here, and 2. That is a special right triangle. It is a 30, 60, 90 triangle. And then if you recall your ordered pairs, your XY ordered pairs here go in the form of cosine, comma, sine. So to find the ordered pair associated with the sine of x at pi over 3, your cosine is adjacent, right, over the hypotenuse, so that's where they get the 1/2. And then the sine is opposite over the hypotenuse, so that's where they get the radical 3 over 2. Some of you have memorized your unit circles, so you know, oh, pi over 3 is whatever, that's fine. I like to derive. So anyway, this is stuff that you're supposed to know coming into calculus. All right, so my first step is going to be to find the derivative, because I have to write the equation L of x. To write the equation of L of x, I need a point and a slope of the tangent line. And so that slope of the tangent line is the first derivative. So I'm going to take this equation here. Really, it's just this equation right here. And I'm going to find the derivative of that. So y prime is equal to, remember the derivative of sine of x is negative cosine of x. So we have to find negative cosine of pi over 3, because our x is pi over 3, right? And according to our ordered pair here, I don't know why I put a negative. My bad, sorry. The derivative of sine of x is just cosine of x. The derivative of cosine of x is negative sine of x, so I apologize for that. All right, so then the cosine of pi over 3, right here, remember x is our cosine, so that's our 1/2. So that equals 1/2. So that is the slope of our equation. So now we have the slope of our tangent line. We need our ordered pair. So to get our ordered pair, we're going to use the original function that they gave us. So for your point, you have to use the original function. So the x value that they gave us for our point is pi over 3. So our point, our x value is pi over 3. We are going to substitute that into this function. So y equals the sine of pi over 3. So remember, the sine is your y value, and so that equals radical 3 over 2. So when x is pi over 3, the sine of pi over 3 is radical 3 over 2. So that becomes the y value of our ordered pair. So our ordered pair comes from the original function, and then we take the derivative of that function and we get the slope of the tangent line. So now we have a point and a slope, and so we can use y minus our y value is radical 3 over 2 equals our slope is 1/2 times x minus our x value is pi over 3. All right, we're going to solve this equation for y, but first I have to distribute that 1/2. So I get y minus radical 3 over 2 is equal to, and maybe in this equation we won't distribute the 1/2. Maybe instead it'll be a lot less work and a lot less steps, because in calculus it doesn't really matter. Maybe instead we'll just move and we'll add radical 3 over 2 to both sides. We'll leave this just as it is and add that rad 3 over 2. So y equals, and instead of y equals, I'm going to put L of x equals 1/2 x minus pi over 3. And I'm adding that radical 3 over 2 to both sides, so plus radical 3 over 2. So there's our linear approximation equation. And then we're going to substitute in the value that we're approximating. So we want to find the linear approximation for x equals 1.05. So here's our x here and here. So L of 1.05 is equal to 1/2 times 1.05 minus pi over 3 plus square root of 3 over 2. So throw that into your calculator and you get L of 1.05 is approximately equal to 0. I'm going to go out to several decimal places. 867426. And the reason why I'm going out to so many decimal places is if we were to do our error analysis, I would want to have as many decimal places as seems reasonable to come up with that. But we are not doing part B. So we're not going to focus on that part. So now in example 4, we're going to follow the same process as we did in example 3. So they gave us, to find the linear approximation to y equals 2 to the x, so that's our original function at x equals 3. So we're going to use that 3 and substitute it into the original function to find our point. So let's just go ahead and do that now so we don't forget. So f of 3 is equal to 2, and let me change that 3 to a red value, 2 to the 3rd, which is equal to 8. So our point is 3, 8. Okay? And then we have to use the tangent line to estimate x at 2.97. So 2.97 is really close to 3. Very, very close to 3. So we should be able to get a pretty close approximation. So I've got my point, I need my slope. So I need to find the derivative of 2 to the x. So if you recall, the derivative of 2 to the x is as follows. Let me use red. So f prime of x is equal to, so the derivative of 2 to the x is 2 to the x times the natural log of the base, which in this case is 2. So then to actually find the value of the slope, because the derivative is the slope of the tangent line, I have to find this value for x. Well, remember, we're letting x be 3, so we're finding it at x equals 3. So f prime of 3 is equal to 2 to the 3rd times the natural log of 2. And I want to keep the exact value, so f prime of 3 is equal to 8 natural log of 2. So we're going to use this point and this slope to find our Lx, L of x. So y minus, my y value is 8, equals, our slope is 8 natural log of 2, so I'm using that point slope form, times x minus, and my x value is 3. And then I'm going to solve for y, and then my y becomes L of x, so I'm solving and substituting at the same time. And all I'm going to do is add this 8 over here to both sides. And we end up with so we've got 8 natural log of 2 times x minus 3 plus 8. So that's what we're going to use to approximate. And then we are going to substitute in 2.97 into this function and see what we get. So I've got L of 2.97 equals 8 natural log of 2, and then that's all times, I'm going to use brackets just because, 2.97 minus 3 and then plus the 8. So if I were you, I would probably put this in my calculator first, then multiply it to the 8, and then times the natural log of 2, and then add 8. When you do that, you get it's approximately equal to 7.833, and I really want you to put it into your calculator to see if you're getting the same value, because if you're not, we need to find out what you're doing wrong. So that is our approximation of the natural log, and actually we know that 2 to the x, or 2 to the third is equal to 8, and look at how close we actually got. So we didn't do too badly there. All right, here we go. Example 5. So for this example, we're going to approximate 2.01 to the 5th. Now I know that you could use your calculator to do that, but we're assuming that we don't have use of our calculator. So you are going to use your calculator to find the accuracy of the approximation though. I'm going to approach this very similarly to how we found the approximation of the square root of 80. So for instance here, we know our function, right? But they didn't say at x equals whatever. So we're going to pretend like this is our actual number that we're trying to approximate, 2.01. So we're going to choose a value that is close to 2.01 that would be easy to raise to the 5th power. So let's start off with, first of all, finding our function. So if I cover this up, we're taking something to the 5th power. So our parent function has to be, our parent function f of x has to be x to the 5th. We're taking something to the 5th power. And so I want to find the derivative of that function, right? So the derivative of f of x is equal to 5x to the 4th. So our a is, well, let's start with our x. So our x is the number that we're approximating. So our x is our 2.01. A is the number that's really close to 2.01, but is easy to work with. And so I would think that our a here should be 2, because I can easily take 2 and raise it to the 5th power. So we're going to use that general form of L of x, a function in terms of x, is equal to f of a plus f prime of a times x minus a. So we're going to substitute everything in here. And so I get L of x. Well, we're going to do L of 2.01. We're going to go ahead and substitute everything all at once. So L of 2.01 is equal to, our function is x to the 5th power. So our a is 2. We're going to take 2 and raise it to the 5th power, and add to that our derivative, which is 5, and it's in terms of a. So our a, which is 2, is going to be raised to the 4th power. And we're going to multiply that by our x, which is 2.01, minus our a, which is 2. Okay, so I get 2 to the 5th is 32, plus, you have to raise this to the power first, right? So 2 to the 4th is 16, and then 16 times 5 is what, 80? So then this becomes 80 times 2.01 minus 2 is 0.01. And so when you finish all that up, let's see, 80 times 0.01 is 0.8. So 32 plus 0.8. So that means our approximation, L of 2.01, is approximately equal to 32.8. 8. And if you take your calculator and put 2.01 and raise it to the 5th power, just as an aside, so 2.01 raised to the 5th power is exactly equal to, well, hopefully it is, 8080401. And so this is pretty darn close to the actual value. Now, we're not going to determine the over or under approximation or the error, so we're done there. So any questions on your homework that ask that, you're going to ignore them. All right, so let's look at example 6. Find the linear approximation to g of x is equal to the cube root of x. So we have been given our parent function and the value at which we want to find it. So we can easily find our ordered pair. So let's start there because we want our ordered pair. So g of 8 is equal to the cube root of 8. So the cube root of 8 is equal to 2. So our ordered pair is going to be 8, 2. So that's our x and our y value. And then we want to find the derivative of our functions. So g prime or g of x, remember, can be written as the cube root of x is written as x to the 1/3. Right? So if I want to find the derivative, so g prime of x would be equal to 1/3 x, and then 1/3 minus 3/3 would be negative 2/3, which is equal to 1 over 3 times the cube root of x squared. Okay, so there's our fun derivative. And then we have to find the value of that derivative at 8. So g prime of 8 is equal to 1 over 3 times the cube root of 8 squared. Okay. Equals, I'm going to change my color so we can see what we're doing here. So 1 over 3 times the cube root of 8 is 2, squared is 4. So it actually gives us 1 over 12. So we have our slope and we have our point. So now I can write L of x. Whoops, I don't want to do L of x quite yet. So we're going to do y minus, my y value is 2 equals, my slope is 1/12 times x minus, my x value is 8. I'm going to solve for y by adding 2 to both sides, and I'm going to replace y with L of x. So L of x is equal to 1/12 times x minus 8, all of that plus 2. And then we want to find, and here's we have to go on and read our problem. So use the linear approximation to approximate the value of the cube root of 10 and the cube root of 16. Compare the approximate values to the exact values. We're not going to find the error of our approximations. So let's find L of 10 or L of 10 and L of 16. Okay, hopefully I can fit all that in here. So let's put this right here. So our L of 10 would equal 1 over 12 times 10 minus 8 plus 2. So 10 minus 8 is 2. So times 1/12 is 2 over 12, which is 1/6. So it's 2 and 1/6, which is 13/6. 13/6 is approximately equal to, decimal wise, 2.1666. Okay, so there's L of 10, and then L of, we'll find those exact values in a minute. L of 16 is equal to 1/12 times 16 minus 8 plus 2. So 16 minus 8 is 8 over 12 gives us, what, 2/3 plus 2, so it's 2 2/3, so that's 8/3. So that equals 8/3, which is approximately equal to 2.666. Oh, isn't that interesting? 666. So then if we found the actual cube roots, so let's find the cube root of 10. Cube root of 10. So the cube root of 10 is 2.1544. So I'm going to put that, let's put underneath here, the cube root of 10. I'm going to put the exact value, well, the exact approximations. 2.1544. Notice that we came up with 2.16 versus 2.15. That's pretty close. And then the cube root of 16. All right, so cube root of 16 is 2.5198. So 2.5198 versus 2.666. So this is a little bit further off, but still pretty darn close. So you can see that our linear approximation does get us fairly close to where we want to be. All right, so we are not going to do example 7, so I'm going to skip on over to example 8, and example 8 will be our last one that we're going to do. All right, so last page of notes, last example. So for example 8, we're going to find the linear approximation for f of x is equal to 1 over x minus 1. And they have given us the x value, x equals -1. So there's no parent function here. We're going to find the ordered pair, and then we'll find the approximation at the -1.2. We are not going to calculate the error of approximation. So we're going to start off by finding our ordered pair. So f of, just trying to save room here, f of -1 is equal to 1 over -1 minus 1, which equals 1 over -2, so -1/2. So our point is going to be, maybe I'll do it this way. So our point is going to be -1, -1, oops, -1/2. Oh, I'm running into my commands for my videotaping. So that's really a -1. It's hard for me because I'm running into some of my commands. Well, maybe I'll move this down. See if it'll move with me. Yep, perfect. All right, so let me try to make that prettier. That's a -1. Okay, so then I need to find my derivative. So to find my derivative, remember that my f of x can be written this way. X minus 1 to the -1. I'd prefer not to do the quotient rule. So f prime of x is equal to -1 times the derivative of the inside, which is, well, -1 times x minus 1 to the -2. So we got to use the chain rule. Then times the derivative of the inside, which is just 1. So this becomes our derivative. And then let's go ahead, I mean, we could, yeah, let's go ahead and write it its proper way, which means that it is equal to -1 over x minus 1 to the second power, right? Then I want to find f of -1 because that derivative is our slope. So I need to have the value of the slope, and we're doing it at -1. So we've got -1 over, and then -1, which is equal to, so we get -1 over -1 minus 1 is -2, squared is 4. So our slope is -1/4. So we have a point, -1, -1/2, and our slope -1/4. So we can now write our equation. So y minus, and then a -1/2 equals our slope -1/4 times x minus -1. So we're going to take care of all of our double negatives. So the double negatives become a great big plus, and then we're going to subtract the 1/2 and substitute in L of x for y. So I get -1/4 times x plus 1, and then minus 1/2. All right, so now I want to find the approximation for -1.2. So I'm just going to substitute that into here. And then instead of this, I'm going to use this part down here. So L of -1.2, and that is pretty close to -1, so we should get a good approximation. Okay, so then I get -1.2 plus 1. Whoops, clearly I put something in wrong. -1.2 plus 1, much better. Then divided by -4, and then minus 1/2. So I get L of -1.2 is approximately equal to -45/100. And that's it. So if you have any questions, please feel free to text me.